Hello everyone, thank you so much for attending our monthly Tech Talk seminar. We are extremely excited today to have Dr. Hubbard from University of Pennsylvania to discuss research with electronic health records data. But before I introduce our speaker, let me go over some housekeeping issues. As you know, we will continue extending CME credits for our Tech Talks and our ID series presentations. We will distribute the information via email to those that registered for today's event. If you did not register prior to today's talk, you can still obtain CME code information from Lisa Maturo at ChristianaCare. Her email address is lisa.m.maturo@christianacare.org. Our next ID series will be on November 13th with Dr. Greg Dobler from University of Delaware, and he will talk about data science-driven projects in public health. And so this will be really very fascinating. Please do not miss it. And we don't have a next Tech Talk yet, but please, we'll keep you posted about the next Tech Talk. So again, we are very excited to have Dr. Hubbard here. Dr. Hubbard is currently full professor in the Department of Biostatistics, Epidemiology, and Informatics in the School of Medicine at University of Pennsylvania, and also Deputy Director of the Division of Biostatistics in the same department. She obtained a PhD in Biostatistics at University of Washington in Seattle, has received many awards, the last one in 2020 when she received the American Statistical Association Health Policy Statistics Section Mid-Career Award. Since 2017, she has been the associate editor of the Journal of Pharmacoepidemiology and Drug Safety. She's a teacher, has mentored numerous students, postdoctorate fellows, and faculty. And she also has multiple peer-reviewed publications and several book chapters. She's a very popular speaker nationally and internationally. We are therefore very lucky to have her today giving us a talk, and also very excited about the topic as most of our analyses are based on EHR. So thank you so much, Dr. Hubbard, to be here and to give us this presentation.
Thank you so much for the warm welcome and the nice introduction. Thank you for having me. So I'm going to talk about some of my research on methods for using EHR-derived phenotypes to conduct health services and epidemiological research. And my perspective is that of a biostatistician. So I'm going to talk a little bit about what I think specifically biostatistics can contribute to research on this topic and how I think biostatistics complements some of the other disciplines that work in this area. As I'm sure you know, there's a lot of enthusiasm right now about conducting research with electronic health records and so-called real-world data. In this talk, I'm not going to refer to real-world data too much, but real-world data broadly encompasses all of the data sources that we're sort of accidentally creating by virtue of the fact that we do everything electronically now. So I think of it sort of as the digital exhaust, the digital footprint that we leave behind as we're conducting electronically mediated interactions. Because electronic health records are now the way that we're documenting medical care, they're one of the first and most prolific sources of real-world data that people have been really interested in conducting health research with. So a lot of the comments I'm going to make, I think, apply to other real-world data sources as well. And I sort of think of EHR data as being the first use case that we've really explored for real-world data. Historically, statisticians have been kind of hesitant and kind of nervous about conducting research using EHR. And clinical informaticians, by contrast, have played a really key and leading role in facilitating the use of EHR data for research. So I'm going to try to stress, for one thing, that I think conducting research using EHR data is really a team sport. It takes multiple different perspectives, multiple different disciplines. And clinical informatics, I think, is absolutely key to deriving meaningful data and making sure that we're using the data in a sensible way when we're doing this kind of research. However, statistics also contributes a really important piece of the puzzle, which is what I'm going to focus on in my talk today. And I think it's really, really important that statisticians in this research context, I think that we do a key. As I said, statisticians have been kind of nervous about getting involved in EHR-based research, and I think that that derives largely from the many imperfections that exist in these data sources. And it sounds like this is an audience that has a lot of experience with working with EHR data, so I'm sure that you all know many of the challenges of working with these data. So this figure kind of relates to my perspective of data science and EHR-based research as a team sport. So here we have different tasks that I think of as contributing to data science. We have the analysis piece, the deriving data from various data sources piece. Maybe we're doing some primary data collection to augment those data sources, and so on. And you can think of all of these different disciplines represented on this slide as contributing to that research enterprise. But the piece that I think is really key as far as the contribution of statistics goes is that we're not only contributing to the analysis, we're not only making use of these data sources, but we're pulling in information, which here is called facts, about the data generating mechanism. Where did the data come from? Why do they look the way they do? And how does that impact the validity of our analyses? So that's really what I'm going to talk about today, is how that piece of understanding data provenance, understanding where the data comes from, can be incorporated into our analyses in order to avoid bias and improve the validity of our results. This is a figure from Google Labs that illustrates the complexity and the messiness of EHR data. And as I said before, EHR is one subset of real-world data. Claims data, I feel like, really goes hand in hand with EHR data. It has slightly different strengths and weaknesses, but a lot of the comments that I'm going to make today are sort of equally applicable to claims-based research as well. And I'm happy to talk when we get to questions at the end about kind of what I see as the distinctions between the strengths and weaknesses of those data sources. But in the context of EHR data, we have sort of multiple data streams. So we have data coming from clinical encounters, laboratory test results, medication prescriptions, etc. So we have different types of data, and they're collected at different frequencies for different people, and we have different quantity of data and different quality of data across patients and across providers. So depending on how an individual patient chooses to engage with the healthcare system and their specific constellation of health concerns, their data is going to look really different from another patient's data. So when we extract EHR data and go to analyze it and use it for research, to some extent, it looks like longitudinal observational study data. So we have longitudinal data with repeat measures. We may be able to extract various different outcomes, exposures, and covariates that we're interested in, but it's a really messy, ill-defined longitudinal observational study, because we as researchers have not been able to exert any influence whatsoever on specifically which data were captured, how and when they were captured, and how the variables that we're interested in the most were defined. So unlike a traditional longitudinal observational study, the data generating mechanism and the data capture process is totally outside of our control, and somewhat more concerningly, is often outside of our awareness. So all we know is we've got the data that we've got, the data that aren't there, we don't really know why. We don't know specifically why a patient might have had the series of tests that they did or made clinic visits at the specific frequency that they did. And yet that's going to influence the validity of our results. And we don't want to just pretend that that data generating process has nothing to do with the exposures and outcomes that we're interested in, because that will potentially lead to bias, as I'm going to illustrate. So I like to think of this as observational research on steroids. It's not that EHR-based research has many problems that we haven't encountered before in the context of observational epidemiologic studies. It's just that they're all there all at once, and some of them more severely or acutely than we would traditionally encounter in any single observational study. So my talk today has two parts. With the overarching goal of kind of illustrating that worrying about this data quality and data capture stuff for EHR data is important because it does lead to bias and inferential error if we ignore it. So that's part one. And then part two will be some solutions in the form of a couple different statistical methods that my research group has worked on to try to improve inference when we're using EHR-based when we're conducting EHR-based analyses. And that part will get a little bit technical. I'd like to emphasize that my perspective is that we should always use the simplest valid analysis. So if we're in a context where we can just use standard methods and get a valid result, I think that that's fabulous, and I would definitely advocate for that over doing some kind of super complicated, fancy statistics that require specialized software and a bunch of people with PhDs in biostat. So I'm going to show you some fancy stuff, but hopefully we'll also be able to think a little bit about when a simpler analysis would be adequate. There are a number of different problems that result from the complexity and messiness of EHR data. The specific challenge I'm going to focus on today is that of phenotyping error. I'm going to use the term phenotype broadly, really broadly, to just refer to the collection of observable characteristics describing a patient. And most of the time in EHR-based research, that phenotype is going to be our outcome of interest. So we've got a collection of EHR data. We want to describe some outcome for our patients, and we need to extract that from the EHR data via a combination of, say, diagnosis codes, procedure codes, laboratory test results, and so on. There's a lot of work on EHR-based phenotyping, and it's been motivated by the fact that for most phenotypes, for most patient characteristics of interest, EHR data don't quite give us a gold standard. And depending on specifically what phenotype we're interested in looking at, sometimes we might be able to use codes or labs to get pretty close to a gold standard. It might look pretty close to what we would have specified if we'd been designing the data collection ourselves. And other times it'll be pretty far away, and we'll really be using something that's kind of an imperfect proxy for the outcome that we really wish that we had. So EHR-based phenotyping is essentially the method of deducing a characteristic of interest that was not explicitly recorded in the EHR data. The complexities of the data provenance process, that process of making visits and having different data elements recorded for each patient, create challenges for phenotyping, and those challenges and the resultant imperfections in phenotyping translate into challenges for subsequent analyses using EHR-derived phenotypes as outcomes. So there are many different approaches to EHR-based phenotyping. Some of them are very simple, like we're just going to look at the records and look for two occurrences of a diagnosis code of interest. Some are very complex and include supervised learning approaches, machine learning approaches, and so on. But regardless of whether we're doing something simple or something fancy and complicated, the bottom line is at the end of the day, we're going to end up with a phenotype that is imperfect. It's not going to have a 100% accuracy, a one-to-one correspondence with the phenotype that we really wish we had observed. So that puts us into the realm of outcome misclassification. Our phenotype is imperfect. And we need to worry about that a little bit, depending on how substantial those imperfections are. I'm going to use as an example throughout most of this talk data from a study that was called BRAVA that was conducted at Kaiser Permanente, Washington. So one of the objectives of the BRAVA study was to develop an EHR-based algorithm, a phenotyping algorithm for second breast cancer events in women with a personal history of breast cancer. So we had a cohort of about 3,000 women who had a diagnosis of breast cancer, and we used their EHR data to try to develop an automated algorithm to determine if the woman had had a second breast cancer event, which we defined as a second primary breast cancer or a breast cancer recurrence. In addition to trying to develop this automated algorithm based on the EHR data, all 3,152 women a gold standard outcome for second breast cancer events as well. So for everyone in this data set, we have a gold standard SBCE phenotype, and then we also have an automated EHR-derived phenotype. We developed what was called a menu of EHR algorithms using classification and regression trees. And each of the different algorithms prioritized a different aspect of sensitivity or specificity or PPV. So a researcher using these algorithms could take a look at the paper, and depending on the specific context and what they were interested in doing with the SBCE phenotype, they could choose which one was most appropriate. For the purpose of this talk, I'm going to focus on just one of those algorithms, which we called the high specificity algorithm. So this was a CART-derived EHR-based phenotype where we prioritized trying to maximize specificity at the expense of sensitivity. So this particular algorithm had a sensitivity of 88%, so we captured 88% of the true breast cancer recurrences, and a specificity of 99%. So we only had 1% false positive SBCs indicated in this data set. When you look at different EHR-based phenotypes, performance varies across these different algorithms and the specific disease context that you're looking at. But in general, a sensitivity of 88% and a specificity of 99% is a pretty good EHR phenotype. That's better than a lot of the ones that you see out there in the literature. It's at least as good as most of them. So this was a phenotype that appeared to perform pretty well based on our manual chart review validation. However, the question that I was really interested in was, this seems pretty good, but if we take this and we put it to use, if we take the EHR-based algorithm and put it to use as an outcome in subsequent analyses, how much bias is going to result in our parameter estimates? So are we really going to end up getting wrong answers, and how wrong are our answers going to be if we use this phenotype instead of the gold standard? Because we had the gold standard outcome for everyone, that provides the opportunity to do some statistical methods, exploration and evaluation, because we can compare the answer that we get when we use the real outcome to the answer that we get when we use this imperfect algorithm-derived outcome. This is just the actual regression tree for the high specificity EHR phenotype for SBCE. So if you look at the nodes in this tree, you can see that they make sort of logical sense. So we're basically looking at a woman's EHR data. We're looking to see if she has subsequent codes for malignant neoplasm, whether she has cancer registry records for breast cancer or another cancer, and what types of surgical procedures she has for breast-directed surgeries. So what we did was use this tree to make binary classifications as to whether or not the woman had experienced an SBCE, and we also used it to assign estimated dates of second breast cancer events. Because, of course, in this kind of context, most of the time, we're not just interested in saying yes or no, did someone have an event? We'd like to be able to look at the timing of those events. So, who had an SBC early versus late. The way that we assigned timing of second breast cancer events in this data set was to just give people the date of the second breast cancer event that corresponded to the node that resulted in them being classified as having had a second breast cancer event. So, for instance, if you end up in this node here where you're classified as having an SBCE because you had a second breast cancer record in the cancer registry, then we would assign you the date of that record in the cancer registry, and so on. We looked at some fancier, more data-driven approaches to assigning the dates, and it turned out that this kind of simple, logical one performed the best, so that's the one that I'm going to show you results for. So using that approach, we assigned these algorithm-based dates of SBCE for all the women in the data set, and for the women who had actually experienced a second breast cancer event, so our true positives, we then looked at the discrepancy between their true SBCE date based on chart review and the date that we estimated using our algorithm. So the histogram here is showing the distribution of the discrepancy between the true date and the algorithm assigned date. And you can see there's this nice spike around 0 days of discrepancy, which is great. That's what we were hoping to see. And in fact, 82% of the SBCEs were assigned a date that was within 60 days of the algorithm base, or assigned a date that was within 60 days of the true date. So most of the time we were getting the date right to within 2 months, one way or another, which is pretty good. But this distribution, for one thing, has really long tails. So if you look at the x-axis on my graph here, I've actually truncated the x-axis at negative 1,000 and 1,000 days of discrepancy because there were a few events where we actually got the date that wrong. We were off by several years. And even though 82% assigned within 2 months sounds relatively good, I think the question that naturally arises is whether or not that's good enough. Is getting the date in a time to event analysis with the kind of rates that we see in this example correct to within 2 months good enough, or is that really going to result in bias in our analyses? So to investigate that question, we conducted a simulation study for imperfect time to event outcomes motivated by the data from the BRAVA study. So using the real data from the BRAVA study and from our algorithm-defined dates of SBCE, we were able to look at the distribution of the error in the dates, the distribution of the true times to event, and the real strength of association between some predictors of interest and those outcomes. And the kinds of predictors that were of interest in this study were primarily comorbidities and medications for common comorbidities. So the scientific question of interest was really about whether women who were being treated for high blood pressure, high cholesterol, depression, and a few other conditions, whether those conditions themselves or their treatments were potentially associated with longer or shorter time to SBCE. So we took the real data, used it to derive the distribution of these types of events and the error rates, and then we simulated data from those distributions to allow us to manipulate the amount of error, the strengths of association, and so on, and look at what the impact of those error rates and strength of associations were on the bias in estimates that we would derive if we were to use the imperfect SBCE dates in an analysis. The main thing that we wanted to get out of this was looking at how different kinds of error in those algorithm-assigned SBCE dates would translate into bias in hazard ratio estimates in a time-to-event analysis. So we looked at several different kinds of error, basically falling into 2 different buckets of kinds of error. So the first kind of error that we looked at was sensitivity and specificity with respect to the binary classification of whether or not an event had occurred at all. So that's one way that we could be making an error. And then a second way we could be making an error is once we have assigned that we believe a particular patient has experienced an event, we now need to pinpoint the date of that event. And so we varied the amount of error in that date assignment as well. The most optimistic case for error of these 2 kinds would be non-differential. So we know that sensitivity and specificity are imperfect. We know we haven't precisely assigned the dates, but in an ideal world, we would at least hope that those errors are not associated with the exposures that we're interested in. So we looked at non-differential sensitivity and specificity and non-differential date error first. However, I'm very concerned about the possibility that in EHR-based studies, depending on the exposures and outcomes that we're looking at, differential error is often quite likely. And so in the specific context of the BRAVA study, my concern arose from the fact that we're interested in comorbidities and medications for common comorbidities, and we're using EHR data to derive the outcome of interest. but women with comorbidities are more likely to have more frequent contact with the healthcare system, which could result in a greater density of data in their EHR, which could lead to either differences in the sensitivity and specificity of our algorithms for women who have the comorbidities versus those who don't, or differences in the distribution of how precisely we're able to pinpoint the date of the SBCE, just because we've got more data for some people than for others. So we started out with the non-differential differential error conditional on exposure status. So we looked at both scenarios where the sensitivity and specificity was non-differential, as well as scenarios where women who were in the exposed group had higher sensitivity and lower specificity of that binary classification. And then we also varied the amount of error in the date, both looking at a non-differential scenario where the amount of error in the date was the same between exposed and unexposed individuals, and then also looking at scenarios where there was differential error in the date depending on whether or not you were exposed. This is a high-level summary of the key results from this paper, and I can summarize the takeaway from this really quickly, which is my interpretation is when you have the amount of error in your time to event outcome that we did in the BRAVA study, if the error is non-differential, the amount of bias that's induced in your hazard ratio is relatively small. So we saw 2.2% bias in our hazard ratio in the non-differential error scenario. What appeared to be the really key factor was whether or not sensitivity and specificity of the binary classification was differential or non-differential. And as long as that sensitivity and specificity was non-differential, the bias stayed relatively low. However, as soon as we moved to a scenario where there was higher sensitivity, lower specificity in the exposed group compared to the unexposed group, we started to see bias move into a range that really has a noticeable impact on your inference. So regardless of whether the error in the exact date that we pinpointed for a woman was non-differential with respect to exposure or differential, as soon as we moved to the scenario with higher sensitivity, lower specificity, we started to see bias in this greater than 5% range. And, that makes sense. If we are systematically capturing more events for exposed individuals than for unexposed individuals, it's clear that that's going to induce bias in our parameter estimates. The question I think is really relevant is how much do we expect that sensitivity and specificity to differ between exposed and unexposed? Because we could drive this bias up sort of as high as we want, depending on the magnitude of this differential and this classification. So this is really just kind of a consciousness raising exercise to make everyone aware, if you're in a context where you think that there might be exposure dependent differential outcome misclassification, you can get bias that's essentially arbitrarily large. So you really do need to be concerned about it. And I'm going to talk about methods coming up for accounting for this because I think it's a significant problem for EHR-based analyses because all patients aren't experiencing the same density of healthcare encounters. They aren't having the same variables recorded. So there really is the potential that across patients, we're going to have our phenotyping algorithms performing differently, potentially in an exposure-dependent way. So that's my bias example. The second piece that I'm going to show you as far as the type of errors and the types of lack of validity that can be introduced into EHR-based analyses is this simulation study that we also conducted based on the BRAVA data, where we looked at the magnitude of type 1 error that results due to phenotyping error. So I think that type 1 error is of particular concern for EHR-based analyses for a couple reasons. One is we're often doing rather hypothesis generating or screening studies using EHR data, where we're potentially going to look at a bunch of potential exposures and try to identify some that we think look potentially associated with an outcome for follow-up in future studies, perhaps using primary data collection or even a randomized trial. In that kind of setting, if we're identifying dozens and dozens of spurious associations, we're really just wasting our time, and we're wasting the time of the people downstream from us who are conducting the more rigorous studies using primary data collection. So as much as possible, we want to make sure that we are mostly finding true signals and not false signals. The other concern is that EHR-based studies often have the potential to be very large. So we can put together databases that include hundreds of thousands or sometimes even millions of patients. And as a result, we can estimate our parameters of interest very, very precisely. That means that if there's even a tiny little bit of bias in our estimate, we're going to reject the null hypothesis, and we're going to have identified a spurious signal because of the fact that we've got such a big data set and we can put such a very, very tight confidence interval on our parameter estimates. So type 1 error is definitely something that we want to think about when we're conducting EHR-based studies, even if we think, well, we're just in a hypothesis generating kind of a setting, this isn't the definitive study, someone else is going to follow this up. Nonetheless, we don't want to be churning out a lot of noise and false positive findings. So in this analysis, what we wanted to do was use the real data from the BRAVA study and then couple that with a simulated exposure that had absolutely nothing to do with the outcome. We just generated it using our computers. And then take a look at, depending on the type of error that we generated in that simulated exposure, how often we would identify a spurious association between our simulated exposure and the SBCE outcome. So I'm going to introduce here this quantity AJK, which just refers to the exposure-specific accuracy of our phenotyping algorithm. So depending on whether J is 0 or 1, AJK is either the sensitivity when J is equal to 1 or 1 minus the specificity when J is equal to 0. So what we're going to assume is that we have an exposure X, and depending on whether you're in the X equals 0 group or the X equal 1 group, you're going to have a different sensitivity and specificity for the EHR-derived phenotype, which here I'm going to call S. So the basic high-level idea behind these simulations is just that using this quantity AJK, we can simulate an exposure X, which is completely independent of the true outcome Y, but does exhibit exposure-dependent outcome misclassification. So we're going to have different sensitivity and specificity depending on X, but X itself is not actually associated with our outcome of interest Y in any way. So if we looked at the association between X, our randomly generated exposure, and Y, the true outcome, what we would find is that there is no association. And so if we were to repeat that analysis and look at the type 1 error rate across repeat iterations of the simulation, we would find that 5% of the time we reject the null hypothesis because we're going to set a 5% significance level in these analyses. However, if instead of looking at the relationship between X and Y, we look at the relationship between X and our surrogate outcome, our EHR-derived phenotype S, what type 1 error are we going to see? Well, the type 1 error that we're going to see in that setting depends on the magnitude of differential outcome misclassification. And so here we've manipulated the strength of differential outcome misclassification by varying the difference between sensitivity in the unexposed and the exposed, and the difference in specificity between the unexposed and the exposed. And we held sensitivity fixed at 0.85 in our unexposed group and specificity fixed at 0.9 in our unexposed group, and then varied sensitivity and specificity in the exposed group to achieve this. For each combination of sensitivity and specificity in the exposed group, we repeated the simulation 1,000 times, and then we averaged the number of times that the null hypothesis of no association was rejected across those 1,000 iterations per scenario to estimate the type 1 error rate. So remember, the type 1 error rate here, the nominal type 1 error rate here is 5%. We're using a 5% significance level. So anything higher than 5% represents type 1 error inflation due to this differential outcome misclassification. This contour plot is illustrating the results of these analyses. And so what we're showing here is the black dot at the center represents the point of non-differential outcome misclassification. So we have sensitivity in the exposed group on the y-axis, specificity in the exposed group on the x-axis, and our black dot represents the point where sensitivity and specificity in the exposed group is the same as sensitivity and specificity in the unexposed group. And you can see if you follow the contours down at that black point of non-differential misclassification, the type 1 error is as we move over the black dot, we're looking at cases where we have higher or lower sensitivity or higher or lower specificity in the exposed group versus the unexposed group. So for instance, if we hold specificity equal in the exposed and unexposed individuals, and we vary sensitivity, so that represents moving away from the black dot in the y-axis. For instance, if we look at the point where sensitivity is 10% higher in exposed individuals compared to unexposed, the type 1 error rate is inflated up to 14%. So rather than the nominal 5% type 1 error rate, we see 14% false positive findings. Similarly, if we hold sensitivity equal between the two groups, and now we move along the x-axis, in the x direction away from the black dot, we're allowing specificity to differ between the exposed and unexposed. And if we allow specificity to differ between the exposure groups by 10%, we see that the type 1 error rate is inflated up to 33%. So 33% type 1 error, I think, is really bad. And this is in the context of a relatively modest sample size. We only had 3,000 patients in this data set. So if we had a bigger data set, if we had 100,000 patients, this problem would be even further magnified. So we've seen that we have the potential for both notable bias and notable type 1 error when we just naively use imperfect EHR-derived outcomes that exhibit differential outcome misclassification with respect to the exposure of interest. So that's kind of the cautionary part of my talk. And now I'm going to give you a couple examples of ways that we can deal with this that are particularly applicable to some of the challenges of the context of EHR-based research. So we've seen we get bias, we've seen that that can induce type 1 error. So how can we fix this? How can we obtain unbiased estimates in association analyses that are using imperfect EHR-derived phenotypes? There are a variety of methods out there in the biostatistical and epidemiologic research for dealing with outcome misclassification, and sometimes those existing methods will work well to deal with the error in EHR-derived phenotypes. And it really depends on a couple features of your specific setting. Specific challenges to using standard methods arise from the fact that often we don't have validation data. So many of the existing methods assume that we have validation data. Sometimes we do and sometimes we don't. But in general, validation data come from manual chart review, which is time-consuming and expensive to conduct. So often all we have are the automated data, and we don't have the opportunity to go back and conduct a validation. That kind of rules out some of the classes of existing methods that are already out there. Another approach that we could potentially use when we don't have validation data is maybe we can't conduct our own validation study, but the phenotype that we're using, someone else developed in their database where they did have validation data, and so they were able to give us estimates of phenotyping accuracy, the sensitivity and specificity, or PPV and NPV of the algorithm. A challenge in the EHR context is the portability problem or the lack of transportability across EHR databases. So often the performance of these EHR-derived phenotypes is better in the database where they were originally developed than in any other database where they're applied. And as people with experience working with EHR data, I'm sure you are familiar with the problem that if you've seen one EHR, you've seen one EHR. Like every practice context is different, has its own patterns, and has their own data recording idiosyncrasies. So it's not surprising that if we take a phenotype from one healthcare system and then we apply it in another healthcare system, it's potentially not going to perform as well. So phenotyping accuracy might be known for one healthcare database, but might be unknown in our specific context and potentially could vary pretty substantially from the healthcare system where it was originally derived. So lack of information or imperfect information on phenotyping accuracy is going to rule out another set of approaches that we might potentially want to use. So I'm going to show you two approaches that my lab has worked on that address different aspects of this challenge. So the first one that I'm going to show you, which I'm going to call augmented estimation, applies in the context where we have some validation data. So yeah, we need to have at least some validation data to use this approach. And I'm going to show you results motivated again by the BRAVA study. And this time, the way that we're going to use the BRAVA study is we're going to pretend that we only have validation data for a subset of our data set. So in reality, we have gold standard outcomes for everybody, but we're going to look at how this method would perform if we only had validation data for a subset of the data set. And we're going to vary the size of that subset. So for everybody, we've got this EHR-derived phenotype, the surrogate S. We have a series of covariates, and then we have our true SBCE status, our phenotype Y, but we're going to assume that that's only available for some smaller subset of our database. The features of this particular approach to dealing with outcome misclassification are, firstly, that it does require some validation data, but it's flexible and can accommodate differential or non-differential outcome misclassification, and we don't have to pre-specify that. So our algorithm is going to adapt to whatever is the structure of the outcome misclassification that's actually observed in the data. That's an advantage over some of the existing methods that assume some kind of explicit model for the misclassification, either that it's non-differential and we can just use a single sensitivity and specificity for everybody, or that there's some specific known functional form relating our covariates, including exposure, to the accuracy parameters. It's also going to improve on efficiency relative to an analysis that only used the gold standard outcome. So if we said, well, we've got validation data for some people, so let's just analyze that gold standard outcome, that has some advantages in terms of reducing bias, but it obviously is going to lead to less precise estimates because we're throwing out a lot of the data. And this is going to allow us, in a data adaptive way, to bring in the additional data that we don't have validation data for. So here's the basic idea of the augmented estimation procedure. We can think of fitting three different models for the outcome exposure association. So X is our exposure, Y is our true outcome. For people in the validation subset that I'm here denoting with capital V, we could regress Y on X and get parameter estimates beta hat V, which would relate the exposure to the true outcome. So we would expect that the beta hat V's are consistent, but they're not going to be efficient because we only have validation data for a potentially small subset of the data set. So we might not like that because we think we're throwing out so much data. This is really wasteful. Let's not do this. We could say, okay, we've got a surrogate for everybody in the data set. So we're going to take our surrogate in the full data set, here denoted with capital F, and we're just going to regress the surrogate on X, and we'll get estimates gamma hat F. Well, those estimates will be more efficient, more precise, because we've been able to use everybody in the data set, but they're potentially biased because S is not Y. S, our surrogate, does not correspond precisely to the outcome that we're really interested in. So model 1, less bias, or precision. Model 2, more bias, more precision. So there's a trade-off there. Another model that we could fit, which is going to seem like, why would you do this? But it turns out that computationally it's a neat trick. We could take the surrogate just in the validation data set and regress that on X, and that would give us estimates gamma hat V. Well, in practice, you would never really do that because why would you take the imperfect outcome in just a small subset of the data set? That's going to have both bias and poor precision. However, if we think about the relationship between gamma V and beta V, if S looks a lot like Y, then gamma V will look a lot like beta V. So depending on how similar, how much correlation there is between gamma V and beta V, that essentially allows us to know how much we can rely on information from regressing the surrogate on the exposure rather than needing to rely on the information about the true outcome. So we're going to use those three pieces, Model 1, Model 2, and that slightly surprising regression of the surrogate on the exposures. We're going to use the information from those three models to construct our augmented estimator, which I'm going to call Model 4. However, before I go to Model 4, I want to introduce Model 3, which is a standard outcome misclassification approach, which was proposed back in 1997 in a really classic epidemiologic paper by Maggie. This is a standard approach to application. This requires that we know the marginal sensitivity and specificity. So to get that, what we would do is just take our validation subset and look at the correspondence between S and Y in that validation subset, calculate estimates for theta and phi, and then plug them into this standard approach. I'll say this paper is way underutilized in analyses of EHR data. If you're in a setting where you do think that the outcome misclassification is non-differential, this approach from this American Journal of Epidemiology paper can be implemented without any specialized software. It's pretty straightforward. I have code on my lab website that consists of about maybe 10 lines of R code that implements this approach, and it will give you valid estimates when you're in the context of a non-differential outcome misclassification. So it's not a magic bullet because it does rely on this assumption of non-differential outcome misclassification, but it's a really nice paper and it's a really straightforward approach that I think people should be using more. So we're going to use Model 3 as a comparison for a reasonable method that we could take when we know that there's outcome misclassification, but we think maybe it's non-differential. And then Model 4 is our proposed augmented estimator. So beta hat A is going to be our augmented estimator, and we're going to get beta hat A through an efficient combination of these three parameters that I defined up here, beta hat V, gamma hat F, and gamma hat V. And basically what we're going to do is look at the correlation between gamma hat V and beta hat V. And those are going to be encoded in these correlation matrices in the middle of this equation. And basically, if they look really, really similar, then that correlation matrix is going to end up being close to 1 if we're looking at a single parameter, or the identity matrix if we're looking at a vector of parameters. And when it's really close to 1, then beta hat V and gamma hat V essentially cancel each other out, and our estimate will just look like gamma hat F. It'll just look like, let's regress the surrogate on the exposure in everybody. And that's because we believe that our surrogate is very close to the truth because gamma hat V and beta hat V were very similar. If gamma hat V and beta hat V look really, really different, then this matrix is going to be close to a matrix of zeros. All of this stuff will go away, and we'll say, we have a bad surrogate. We're just going to rely on beta hat V, the estimate that we would have gotten if we just used the validated outcome in the validation subset. In practice, neither of those two extremes is really going to happen. We're going to be somewhere in the middle. And so what the augmented estimation procedure is allowing us to do is have a data adaptive estimate that will use more information from the surrogate when it looks like the surrogate is good, and use more information from the truth in the validation subset when it looks like the surrogate is bad. And the strength of that, of the accuracy of the relationship between S and Y is not assumed to be non-differential. This data adaptive approach will allow for differential misclassification and will bring in information from the surrogate as appropriate, depending on how good the surrogate looks. So to evaluate performance of these different approaches, I'm going to show you an analysis that we conducted using data from the Bravo study. So we compared the performance of Model 1, which just uses the validation data, so that's going to have low bias but poor precision. Model 2, which uses the surrogate for everyone, so it's going to have poor precision, it's going to have poor bias, but good precision. Model 3 is the standard outcome misclassification approach that assumes non-differential outcome misclassification, and Model 4, the augmented estimator. We looked at 3 different surrogates. So first we looked at the high specificity surrogate, the one that I've talked about up to this point. It has pretty good it has pretty good operating characteristics. So we also wanted to explore a couple surrogates that would show us how these methods work when you have a surrogate that doesn't look so good. So we looked at the high specificity surrogate. Then we looked at a surrogate with poorer sensitivity and specificity, but where those sensitivity and specificity were non-differential with respect to the exposure of interest. And then we looked at a poorer surrogate where sensitivity and specificity were differential. They did vary between exposure groups. So as expected across, and the other thing that we varied here on the y-axis, I'm showing you the number of people in the validation subset. So we varied the size of the validation subset from 400 up to 1,200. In each of these plots, the black dashed line represents the estimate that we get if we regress the exposure, if we regress the true outcome on the exposure in the full data set. So since we had validation data for everybody, we did that regression for everybody. And the black dashed line is the estimate that we got, and the gray band is its confidence interval. So that's not necessarily the truth, but it's the estimate that we would get if we used the best data available for everybody. And we're going to look at how these methods using a misclassified outcome compare to that one. The results for Model 1, I think, are pretty much what you would expect. When you have a small validation subset, you have really wide confidence intervals, and you potentially end up with a point estimate that's kind of far from what you would have gotten if you had the full sample, just due to model instability. We've got a small sample size, and by chance, we come up with an estimate that's kind of far from the truth. As our validation subset gets larger, the confidence interval for Model 1 is going to shrink because we're using more of the data, and our result is going to become more stable and get closer to the full data estimate. Model 2 is very precise. We get a very narrow confidence interval because we're using the full sample. When we have a good surrogate, as we did in the case of the high specificity surrogate, the point estimate looks good. It's quite close to what we get using the validated outcome. When we look at these poorer surrogates, we see pretty notable bias in that estimate that just uses information from the surrogate. And that bias can go in either direction, depending on whether or not we have differential error or non-differential error. Model 3, our standard outcome misclassification approach, markedly improves precision relative to Model 1. So we're bringing in information from the full sample. We decrease our confidence interval width. That's a good thing. In our high specificity surrogate case, the bias looks relatively small. Similarly, when we have non-differential error in our surrogate, bias in the blue method, method 3, is quite small. When we move to the differential outcome misclassification case, bias in method 3 is quite large. And that's because this method makes a fundamental assumption of non-differential outcome misclassification error. It can't accommodate differential error, and significant bias results in settings with differential outcome misclassification. So finally, Model 4, our proposed augmented estimator, it represents a little bit of a trade-off. So we're not going to get as much reduction in the confidence interval width as we would with Models 2 or 3. However, we're able to reduce bias pretty substantially in almost all cases. So if you look across these different settings, we're reducing bias to a pretty good level, whether we have non-differential or differential outcome misclassification, except for in this scenario where we only have a validation subset of size 400 and we have differential error. So in this setting where we have a small validation subset and differential error, the augmented estimation approach isn't really able to tease out the structure of the misclassification, and as a result, we're not able to control the bias very well. So my overall conclusion is the augmented estimation approach gives us a nice trade-off in terms of decreasing bias while also improving precision across all different structures of outcome misclassification, except for the setting where we have a small validation subset and a complex structure to the error in our outcome. And in that setting, we either need to make some assumptions about the structure of the error, like Model 3 does, or more realistically, we just need to accept that we need a larger validation sample in order to be able to use the augmented estimation approach. Oh, I'm running out of time. Okay, I'm going to speed up a little bit and show you the second method that we developed, which is useful in the context where we don't precisely know the operating characteristics of our imperfect outcome. So this approach is called the pi approach. And the idea behind pi is we'd like to estimate parameters relating our exposure to our true outcome, beta, but we didn't observe the true outcome, we only observed the surrogate. And so the probability that our surrogate takes a value of 1, we can write in this mixture distribution approach, which is a combination of information about the relationship between x and y and information about the relationship between y and s. So P here is the information that we actually observed. We can use it to construct this estimate to try to get valid estimates of our parameters beta. The problem is, in order to do that, we need to know the sensitivity and specificity of S. And so there are a couple different things we could do. We could ignore the outcome misclassification, just assume that sensitivity and specificity are perfect and estimate beta. We could try to estimate all of these parameters simultaneously, sensitivity, specificity, and the association parameters. Or we could say, well, somebody previously validated this algorithm and they said the sensitivity was M and the specificity was S, so we're just going to fix those values and then estimate beta. It turns out all of these methods are biased in finite samples. Even this joint maximization approach, which seems like theoretically the right thing to do, but it turns out in a finite sample, you just don't have enough information to simultaneously estimate all of those parameters and get unbiased estimates. So the pi approach, which through a somewhat liberal use of acronyms stands for Prior Knowledge Guided Integrated Likelihood Estimation, the pi approach says the thing we really care about here is beta. Sensitivity and specificity are nuisance parameters. So we don't know what they are precisely, but what if we could put a prior distribution on them and say, well, we think they fall within this general range, and then integrate our likelihood with respect to that prior distribution. That gives us this resultant integrated likelihood, which is only a function of beta, the association parameters that we care about. It's no longer a function of theta and phi, and we can just maximize the integrated likelihood to get estimates for the association parameters that we care about. So since we're putting prior distributions on things, this kind of looks like a Bayesian approach. The difference is we're only going to put priors on nuisance parameters and integrate those out, and then we're going to do a more standard frequentist maximum likelihood approach for the parameters of interest beta. I'm going to show you real quickly results of a simulation study evaluating the pi approach and comparing it to those other methods that I mentioned. So assuming that sensitivity and specificity were perfect, we're fixing the sensitivity and specificity at values derived from a prior study. The really important aspect of this analysis was that we looked at different distributions that you might put on those sensitivity and specificity parameters. So 2 of the prior distributions that we looked at, we used log normal distributions. For pi 1, we centered that log normal distribution at the true sensitivity and specificity of the algorithm. In pi 2, we did not. We shifted our distribution so they were centered at the wrong value, because it's pretty optimistic to assume that we can center our prior distributions on the truth. We don't know what the truth is, so probably we're going to get it somewhat wrong. And then finally, in pi 3, we used uniform distributions, which were also not centered at the true values. The idea here was to say, maybe all we can say about the sensitivity and specificity of our surrogate is we think it lies within a particular range, and that's kind of the best we can do. So we said, well, what if sensitivity, we guess, lies between 0.6 and 0.9, and specificity lies between 0.65 and 0.95, which is a pretty broad interval for both of those. And what we found with this study was, not surprisingly, if we ignore the error in our outcome, we get bias. If we assume incorrect values for sensitivity and specificity, we get bias. And if we use the integrated likelihood approach with any of the 3 prior distributions that I just described, we substantially reduce the bias. And most importantly, using that uniform distribution, pi 3, where we just specified a range that we think sensitivity and specificity lie in, we were able to reduce bias almost all the way to 0. So I see I'm right at time, so I'll wrap up quickly. The main takeaway that I hope I have conveyed is that outcome error, outcome misclassification, phenotyping error really can lead to meaningful bias and inferential error in EHR-based analyses. So there are a number of things we can do to combat that. We can obtain the best possible phenotypes, conduct validation studies to try to ensure that our phenotypes have the best possible operating characteristics, use appropriate methods, so whether that's standard outcome misclassification approaches for non-differential error or more novel approaches, either way, we need to be accounting for the error that's there to avoid bias. And we need to limit the assumptions that we're making about how good our phenotypes are and whether or not their operating characteristics from one healthcare system apply in our current setting. So, all of these analyses with EHR data really do take a team. We need to have the domain expertise and the clinical informatics expertise in order to have a good sense of what the error in our outcomes look like. And then statistics provide some of the tools, like I've just described, to try to improve the quality of our inference. So I will conclude just by thanking my collaborators who worked on this research, as well as the financial support of PCORI and the NIH. And thank you.
Thank you so much, Dr. Hubbard. I think it really raises so many questions for us, and I think we'll be able to apply in our whole analysis some of the methods that you described. It's just fascinating. I know that we are just right on time, but if anyone has any questions. I think that right now, yeah. So I think we are going to close the session. Well, thank you again. And, maybe at some point we could collaborate because we have a lot of data here.
Yeah, you can always feel free to shoot me an email. I'm very responsive on email. So if you have questions about implementing any of these methods or anything else, I'm always happy to chat by email.
Great. Thank you so much.
Thank you.
Bye. Thank you.
Bye.